My work on this problem consists of two parts. The first one is pretty bad. You'll see me in a situation where I'm really not able to think very well. So the brain is um, unable to do precise analytical thinking. I could get ideas though, but I was not able to carry them through. I've been in this situation occasionally, even at exams, where I've been studying hard up to the exam. So I think it's important to be able to find out what are the symptoms. The brain does not really discover it by itself. So, and when we are tired, then our analytic ability is smaller anyway. So it'd be nice to have some telltale signs to look out for. So the first video, don't see it for laughing at my poor mathematical ability at the time, but try to analyze, is there any signs that you can recognize to be able to distinguish that today is a day you should not try to solve problems. Just enjoy life, relax, try to get your energy up again some other day, not this day, because you are finished, boy. So it's been a while since the last recording. I've been working on Android programming, the modern way of binding data to user interfaces. That was very difficult, but finally today I solved a lot the last problems. So I've been working all day getting one new thing working every half hour. So it's been very gratifying. So now I feel ready to start on the analysis. So let's see what we've got. I actually read this exercise or this problem 1 or 2 weeks ago, and I couldn't help thinking a little about it every now and then. So, so we have an integer n and any function of period n, meaning we have at most n square distinct values. F of naught vanishes, all right. If s equals 2, suppose further that the sum of the numerators vanish, yeah, in each square. Then we define this function. It's very much like the double periodic functions of the chapter, except that they don't subtract the term that actually made it convergent for s equals 2. So converges absolutely if s is larger than 2. It should be an integer, I guess is 3. And if s is 2, and conditionally, okay. Right. Now, if s is bigger than 2, then I think it's dominated by the maximum m, the maximum value of f. So that's question A. And since there are only n squared distinct values, it does attain a maximum. Why did I write B and not draw an equality sign? There we go. So this is dominated by not containing the lattice point. Capital L because the lattice is... Oh, they haven't introduced the lattice. Well, never mind. So they don't prove it very detailed in the book. They say that the number of points in any given circle with the integer radius n and n plus 1 is of the order n, but we need actually to prove that it is bounded by a constant times n. So I don't know if we should do that now or whether we should skip it. I spent a long time on this problem while reading the text, but I think we should just take that for granted and get on with it. So if S is 2, then we really miss the terms that were subtracted in the book. So what do we do? Oh my God, what is Z? It's a function of S only. No Z is involved. Oh. So you see, I read it a week or two ago and I didn't even read it correctly. I was really preoccupied those days. So this is just a series of numbers. So it just converges. Absolutely. Oh, now it's gone blind. There we go. This is difficult. So I can't even write. Let us see if this works. No, it doesn't. So we'll just have to start all over again. So back again. I'll just check that we are going right. So back again. So we just have a sequence of a pair of integers. I hallucinated that Z was in here. And of course, there's no mark for not taking m and n equal to 0. That must be excluded, of course. Oh, that's just, well, never mind. So if s equals 2, it converges, though not necessarily absolutely. So we should be using this sum, of course. So we should try, what should we try? This hint has increasing absolute denominator, but that makes it difficult to use the periodicity of f, and that the sum vanishes. I would like to sum over large n's where like these. First, to see if we can reduce this function. So should we put them all on the same denominator, and then hope that we cancel some terms in the numerator? It might be for that they have said that s should be an integer, because then we can expand this by the binomial theorem. So let's try that. P is not. That's done. Where m and p can be assumed to be multiples of p of n, if we should like that. Now this we call Q. Oh, it's M and N. That's much easier. So it's the product over all of them except M comma N divided by the product of all So time for expansion. I don't know which one we should take really. X to the S. The total power will be X um, will be S. Yeah. And then the product this doesn't seem to work very well. Ha! I'm frustrated at this point. So let's skip A at this point and see if I get any ideas regarding B. The values of, now what is it called? The Weierstrass P or its derivative at points which go in there and there. Well, it's periodic. No, what am I doing here? It's just a number. Now, if we, I don't get any ideas at all. So we'll have to wait until I get ideas for this. So that was it for today. So it's been a month since I solved problem 5.2. In that time, I've been programming an Android app for making payments. It's a project I'm running where I want to make an alternative to paying with the Danish monopoly called Nets, which is pretty expensive as is handling cash. So the point is to use Bitcoin, or rather the Lightning Network on top of Bitcoin as a token, and just letting those circle around, then it'll be practically free. So finishing the app took 4 weeks. So now I'm ready to do mathematics. I did make a try some couple of weeks ago, but I didn't do very well there. Actually, I think I was so tired that the brain just locked down. I could get an idea to solve the first part of problem 3, but I was unable to go through with the details. Then I started looking at 3b, and what you know, they referred to exercise 2, and at the time I'd totally forgotten about it. So let's see how I do today. So what I missed the first time was that naught is actually excluded from the sum, so there's no division by naught. And then my idea was to look at a square for some large m and n. So let's say z equals I should have prepared this lattice beforehand. So I'll just say we have omega 1 here and omega 2 here. So we are far out up here. And then this is our set. And then we'll just be looking at this square. These are excluded. No, that one is solid. That's with, and these edges are excluded from the sum. So we just look at the sum over this square. Oh, I'll just reuse m. And this we just call omega mn. And the only question was what happens when s is equal to 2. So we'll just write 2 here. And then I will show that when we add all these over this parallelogram, then the set, the denominator, will have a power of 2 times capital N squared, and then that the numerator is at least, or is 3 times, yeah, at least 3 times smaller. So that was the idea, and now today I hope I can do the details. So it's the sum of and then this z squared plus 2 alpha omega mn plus omega mn squared. So down here we have the product of them all. To z. And up here we have the product, the sum of products where exactly mn is excluded. So the highest powers so from here we have, this is a total of n squared points. So this is 2 to the n squared plus, and then the sum of these points come times z, etc., being 1 smaller. We don't have to worry about that, I think. And up here, it's the sum of times. And here we have the power of z being 2 less. Plus lower, meaning z to 2n squared minus 3, etc. This is the constant, so the sum here will vanish, giving us highest power 2 times 2 times the sum of nn times all of these. Right. So because the first sum vanish, because the sum of the coefficients vanish, then the first term is 3 times lesser. Its order is 3 times below this. So that means that if we add up such squares, and then adding the squares, then the sum of the squares converges absolutely. That's not what he wrote. He wrote that we should take the sum in decreasing order. And as far as I can see, that would give the same. Because if we have a circle, large circle here, and then see the ones sitting in some larger circle, then it'll just be a number of squares here. So I think that there's summing the way I did and then summing this way will give the same result. So I believe that my idea of solving A was sound, but at the time I wasn't able to do it. So we go to part B. And I tell you, I had to think over this a couple of days. And I was ready to give up and just say, I get absolutely no idea. I hadn't gotten one idea. I hadn't got, it's called. Well, on the other hand, when I looked at the that we should evaluate it with still f in the same lattice, my ideas all were about choosing a larger lattice for the elliptic function, but we have to use the same lattice. So how can we get it down to the same lattice and then points in that lattice? And then one day, eureka, I saw it. I got an idea at least. So now we shall see if I'm actually able to solve it. So this idea I didn't get while recording. I got it some days ago. So we have the sum and my idea was to divide all of these by n. Then we get an n to the s up here. And the next step is to connect it to the elliptic function, to Weierstrass elliptic function. That's a function of z. I just forget the exact definition. It's 1 divided by z squared, z to the s, plus sum of 1 divided by, is it z minus l minus some, z minus l, yeah. summing over the lattice except naught. So how do we connect that? So when we sum, then when we add capital N to both of these, we get to a new lattice point. So that means that what does that mean? That means that we write this with different lattice points so that we, yeah. So we split it up so that we sum over for each N and M, as soon as they hit the same lattice point, that's when they are multiply of capital N, then we are in the same sum. So we split up the sum. And then enter minus S is put out here. F can go out here. And then this and this is mu nu to the S. So it's beginning to look like it. Now we've got this and this. There's just one thing. I actually did see that coming, that subtracting the lattice points now. If S is bigger than 2, then we can split it up. So let's do that for the moment. Now, what did I do here? It should be divided by n. So these terms are, I'll just point it better. These terms take the ones I've indicated here. And then we have to add this. And this is assuming s is larger than 2. And now my point here is that this and this is constant, so that will vanish. My God, I'm through. I was really willing to give up on this problem. So how do we do about case s equals 2? By the way, isn't it obvious that the derivative won't occur? No, it's not. It's not a function. This is just a number. Well, well, well. Well, guys, I'm glad I made it this far. The special case s equals 2, I'm not sure about. But when s is larger, then I find it pretty sure that I've done it. So, thank you. So, once again, a week after the first recordings, I'll have another go at exercise 3. I woke up this morning 5:30 thinking, well, this is early, I should sleep some more, but I couldn't. Then I eventually thought a little about this exercise, problem 3, and then I realized that it's stated explicitly in the, I didn't realize, I got the idea that it was only for integer values of s, because then we could compare the sum to the derivatives of Weierstrass p function. That would only hold for integral or for positive s's, s larger than 2 being 2, 3, 4, 5, etc. And then when I got up, having had breakfast, I looked at the exercise and it says explicitly that s is a positive integer larger than 1. So let's have another go on the exercise. So I prepared by writing up a formula from the last recording. This is the sum we are working on, and I was able to transcribe it into this, where m is written y times capital N plus mu, where mu only goes up to the sum becomes n minus 1, and then we increase y. No, I. The same with n. Then we get this sum. And we should compare that to the derivatives of the Weierstrass p function. So the first derivative equals minus 2 I'll just check this. Right, that's page 17. The second derivative, I'm not good at this, p, that gives plus 6 to the fourth, the third, minus 24th, and the denominator to the fifth. So now we can write up the nth derivative. This will be the, first the sign, minus to nth, and then this is n plus 1, the faculty of n plus 1. Oh, I'll just write it as a fraction. To s plus 2, n plus 2. So this should be very easy to prove by induction. And then we have to compare it to this sum. This will be our set and the lattice. We're running through the lattice. The sign is irrelevant. And then the only difference is this. So it becomes n to minus s from the original sum minus n to the nth. This is the gamma, or I could write it gamma of n, but we'll just do the faculty. I wonder what it's really called. I've heard it, but I forget it. And then it's s minus 2 . Oops, then we have these sums. So we'll have to write this as a sum out there. I wonder where my eraser is. I think this is an eraser. It was, though not very effective. This may be a better eraser. It was. And the pen, let's go black. So this is my solution. And I hope that this really solves the exercise or the problem.